Welcome, everyone, to the 119th meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Mikhail Bondarko from St. Petersburg State University, and the title of his talk is on periodic objects and semi-orthogonal decompositions corresponding to exact transformations. Please go ahead, Mikhail.
Okay, so thank you very much for giving me the opportunity to give this talk. So this is rather new material, so I'm not sure that I will present it in the optimal way. And your suggestions are very welcome. In particular, maybe I will change some terminology soon. So I did it quite recently, in particular. Okay, and a large part of my talk is very basic category theory. And my current impression is that even in this case, we obtain something new, but maybe I'm wrong. Maybe somebody did this, I don't know, 40 years ago. Okay, so we start with some category C underlined, and we have some endofunctors on this category. And usually C underlined we will triangulated, but in one case I will need an embedding category, and it works quite generally. Now, so we have some transformation between these functors for each index. And now our main hero is a class of so-called T-periodic objects. So it means that for X is periodic if the functor it represents, since all the morphisms coming from T on C into bijections. And so I would like to say that it makes sense to describe periodic objects in a certain way. And also we are interested in the case where there exists at least one adjoint to the embedding of the subcategory objects into C itself. And so in the triangulated setting, if you have some embedding, then you have a so-called semi-orthogonal decomposition. So another term for this situation is Boosfield localization. And now I will introduce some other related classes of objects. So for a class of transformations like it was above, so I call an object, I say that it's universally divisible with respect to T if just all these morphisms are invertible. So I'm not sure that this is the last version of my terminology, but I will just justify this soon. And also, so cone of T means that you take all your transformations, all objects, and consider cones. So this is notation specific to triangulated categories. Now, in the triangulated setting, I always assume that the functors we are considering are exact, and I also assume that transformations compute with the shift, at least in some weak sense, And maybe possibly I will call these sets of transformations of the sort truly exact. And in this case, the periodic objects are just given by the orthogonal to the class, to the cone of T. And so the orthogonal is defined as follows. So we take the class of those objects such that there are no non-zero morphisms from cones to them. Now some examples that motivated me. Roughly, I would say that if you have a transformation of this sort, then it appears to be rather reasonable to assume that so your functors leave are objects of some certain category, and transformations are morphisms in this category, and it means, and then so you may say that your transformation is tensoring is given by tensoring by some morphisms. And so if you have a reasonable triangulated tensor product, so it can be internal tensor product or some external tensor product. So you will soon have an external example, but if it's reasonable enough that you obtain transformations. Okay, so I didn't say any assumptions in the general case, but so under certain very reasonable axioms, you will get truly exact transformations from morphisms of like this, if you do like this. And so now if your category is monoidal, then you can just tensor to obtain the cone. You can just tensor objects by cones of this morphism, certainly. And then you have some motivic examples that are really important for motives. So I just listed them, and I will not say much about them. So there's a paper of Bachmann that says that you can construct, study the so-called real realization using so you should look at periodic objects with respect to a single transformation. And it appears that in the motivic, okay, in many cases, including those relevant for motives, you consider transformations from identity or the same thing into identity into tensor invertible objects. Okay, so this is the case in this setting, and in particular, you can. Oh, I forgot to write SH here. Sorry. So I will add it now. So if you take the stable homotopy category, and invert rho in a certain sense, then you'll get the usual topological state. So you take the motivic state homotopy category over R over real numbers and invert rho, then you will get the usual stable homotopy category. So what does it mean? Inverting, so in this case, this is more or less equivalent to considering a left adjoint to the embedding of local objects in the whole category, and I will speak about adjoints of this sort later in my talk. Okay, and there is another paper so that gives a similar result for Voevodsky motifs, and actually this guy is not in tensor invertible in the effective category, but it is tensor invertible in the bigger category. I believe that there exist several variations of this result. To my surprise, I wasn't able to find these formulations, but I believe that they exist, and in some of them, so you can, so certain assumptions from K probably they can be weakened, and you can probably get rid of F here, and then you will get morphisms between invertible objects. Okay, and now the term periodic, so I'm not sure, but at least I found it in this paper. And so in contrast to my talk, so this paper gives a description, so under certain assumption on transformations, it, okay, so it, I think transform, okay, matter. So it's the results of this section say that you can invert transformations using certain homotopic limits. So rather than natural formulation, but the question is when it works. And so now I will soon pass to the setting where you can just difficult to formulate it. Okay, so I have some R-linear examples. So we have an R-linear category. R is a commutative ring. And the most simple transformations are just multiplications by some scalars. And you may say that that your ring is a category with single objects, and this is a tensor category, and you certainly this object is invertible, so you don't. It's rather simple case if you try to apply say these results. But you can also now so why universally divisible? That's because the periodic objects. In this case, the periodic objects with respect to this T are the same thing as universally divisible objects. So this is an easy exercise and also follows from some statement that I will formulate below. And these universally divisible objects are precisely those where the multiplication by elements of S is invertible. Okay, so it's quite natural to call them universally divisible. Maybe this is not so natural to use this terminology in the more general setting. Okay, but so and then this localized ring acts on the object of this category. Now you can also define more general actions. So if you have arbitrary coproducts, then you can multiply tensor your objects by free R modules. Or you can just assume that you have coproducts of some limited size and multiply a tensor by free modules of this with this number of generators. Now, if it's also idempotent complete, yes, so closed with respect to passing to formal direct summons, Karobin also another term. Then you can also tensor by projective modules with the corresponding number of generators. And you can also dualize. So yes, this is a notation for this tensor product defined by means of coproducts. You can also dualize and define tensor product using products. So I invented this combination of symbols. I'm not sure that I will ever use it actually. But so if you dualize, it certainly means that you act by the opposite category. Now, so when you have this, so you have a collection of morphisms between, yes, did I? So collection of morphisms between some projective modules, then you can consider, so you consider transformations that corresponding to tensoring by these morphisms. And we start from defining the corresponding subcategory of R modules themselves. And okay, so you have some. So how can you describe it? You can describe it using just definition. Now, since you can easily reformulate it like this, so you should look at certain orthogonal is derived category. And so if your complex splits as the kernel and the co-kernel, yes, then this so this orthogonality means that home between these two modules vanish, the first X vanish, and this home vanished as well. So usually one is interested, one takes Fi to be Fj to be surjective, and then you just have these two home and X1 conditions. Now I have a very recent result. This is quite simple. So the idea that so when is object periodic? So it's periodic if and only if so you can compute the ingredients in the definition of periodic in terms of this module self. So you obtain that an object is periodic if and only if this for any y this object belongs to AT. This module belongs to AT. So this is our module. So I probably forgot to say, I wrote this down, that this is an abelian, exact abelian subcategory of R modules. So you have a very simple criterion. Now, what can you say about this subcategory? There are some older results and a quite recent paper of 5 authors. Okay, and if you combine them, you more or less easily obtain that if you take fj, any collection of fj, so what can you get from collections of morphisms between finitely generated projectives? So you obtain exactly the corresponding subcategories are subcategories of modules over some ring R prime, and R prime is said to be a universal localization of R. So what do we know about this? So this is a commutative ring. Its spectrum is open in the spectrum of R. And so if R is regular, then you can obtain all affine open subsets of its subschemes in the spectrum like this. My impression is that I can obtain an answer in the more general setting, but I'm not quite sure. Okay, so you see, when you took so we have obtained this simple localization modules over the simple localization when you inverted just multiplications by elements of R, and we obtain modules over more general localization if you allow consider transformations corresponding morphisms between projectives. And my impression is that you can, it suffices to consider just a single morphism from R into, from an invertible ideal into R, at least in, maybe under some assumptions. Okay, and I would like to note, yes, so we are interested in the class of T-periodic objects. It is certainly not true that you can recover T knowing periodic objects. You can try consider, I don't know whether it makes sense to recover some maximal T. Maybe it would be something big, I'm afraid. I don't know whether it makes sense. Okay, so but if you know that, so the point, if you know that your class is of objects T is a class of T pre-objects for some T, that then you get some information about this subcategory. So we will see example when you have two distinct choices for T below, but it doesn't mean that one of them is better than the other one. Okay, so now the main tool of our paper that we are writing is quite simple. So it's called conjugate transformations, and it is introduced, at least in McLean's book. Maybe it was introduced earlier, I don't know. Okay, so this is okay. So this is a diagram. Yes. So we have so if you have adjoint functors, then we fix these two isomorphisms of bifunctors, and then the statement that there exists a unique tau lower star that makes this diagram commutative. There are some very simple. Okay, so you can certainly prove several basic properties of this lowest operation. An example, for example, so I believe it should respect compositions in a certain way. Also, probably some coproducts should convert to product, something like this. Okay, and now, so in the exercises that periodic objects with respect to a transformation tau are the same things as universal divisible objects with respect to transformation tau over star. And here is one calculation in the case when you have transformation from the identity to an invertible functor, then you can easily describe the conjugate transformation. And actually, in this case, the tau divisible objects are the same thing as tau star divisible. This basically means that the theory that I will describe today is not very interesting for transformations of this sort. So we passed to the triangulated case and assume that now that I forgot one star here. So that the adjoint functors exist. And as I've said, this automatically implies that conjugate transformations existed as well. So sorry. Okay, so here it suffices to assume that you have adjoints to all these functors, right adjoints, and okay, and now suppose we have some generators in the following sense, that they are orthogonal to this set is 0. Then so I recall that I said that periodic objects consist of the orthogonal to cone of T of the whole category. But in this case, it suffices to consider just apply transformations just to generators and they're shift by -1. Actually, usually one considers generators that are stable with respect to shifts. Yes, then you don't have to add this. Now I will not explain you a T structure, but I hope that some of you heard about T structures. So if these functors are T exact, so the conjugate functors are T exact, then it easily follows that an object is periodic if its T homotopy is periodic. And if T is also non-degenerate, then you obtain an equivalence here. Now this looks maybe a little complicated, but it also we have surjection here and a surjection here, and it's equivalent to having bijections here and here. And you may see once again, so this is some result of this sort that you don't have to consider you don't have to apply your transformations to all objects of your category to check whether the object is periodic. And this will transform into a rather nice statement in the R-linear example. Oh yes, so if you apply this to the R-linear example, now, so recall that to check, I've already said then to check that the object is periodic, you should check that morphisms from any y to x belong to the periodic part, T-periodic part of R modules. And here, so if you use this, then you can reduce it to looking at, so it suffices to look for morphism into X over sufficiently big power of X. So you just need a power that would be not small, bigger than each of these guys. Now I pass to semi-orthogonal decompositions. So a little reminder. Okay, as I've said, this is alternative term is Boosfield localizations. I prefer to say semi-orthogonal decompositions because this term stresses that there is this notion is more or less self-dual. So if you have adjoint to embedding of a triangulated full triangulated subcategory, then one says that the left orthogonal to this subcategory and the subcategory itself give a semi-orthogonal decomposition. So roughly this means that this orthogonal is big enough, and then big enough means that you can decompose each object of your category into a distinguished triangle of this sort. Okay, so here you have certainly a morphism from X from L at X, and then you the cone will belong to the I think right admissible part. Yes, sorry. Now, okay, I will. So we are interested in the case where this left admissible part is the T-periodic objects, and then you can actually note then these objects are also periodic with respect to this obvious transformation. But as I've already said, so you cannot say that this description is better than this description. And I also say a few words about well-generated categories. So I don't want to define this thing. So this definition was given by Niemann. So it was little simplified by Krause, but it's still rather maybe it's not very friendly, I would say. But so there's a much easier notion of complexly generators, and are so well-generated is a bigger class that possesses a better, you may say, possesses better categorical properties. And so there are several important examples of triangulated categories that are not complexly generated by well-generated. And also one of the properties of well-generated categories that I will recall that a functor between generated categories, well-generated categories admits right adjoint if and only if it respects coproducts. Okay, so now I pass to this theorem. So suppose that you have transformations between functors that only between functors respect coproducts. And so I was not, and here it's also important that you only have a set of transformations and not a proper class. Okay, and then this couple is a semi-orthogonal decomposition. And we also have a description of the right admissible class. So this is a certain span of the class of cones. So the smallest triangulated subcategory of C that contains all these cones and goes with respect to coproducts. And I don't know whether it's better to call them T-torsion objects or maybe in T-torsion objects. Okay, but you may say that in this case, so we have true adjoints for the embeddings. So right adjoint to this embedding and the left adjoint to this embedding. And you may say that we have these adjoints are T-torsion parts and T-periodization functor. And I will need some notation for them. And also, if these adjoints respect coproducts as well, then this periodic object subcategory is also a right admissible component of a certain semi-orthogonal decomposition. And so I also give a very vague formulations. So if you have a weight structure that, so in my terminology, I call them smashing, it means that V is compatible with coproduct in a very reasonable way. And if this all these functors are weight exact, or maybe a little worse, so then there exists a weight structure on T-periodic objects such that this functor is weight exact. Recall that so if you have a semi-orthogonal decomposition, that this level, okay, so an adjoint to an embedding is a localization functor. So it's surjective on objects and means that you have at most one candidate for a weight structure such that the LT is weight exact, but so the question is whether this candidate is a weight structure indeed. So in this case, it's a weight structure. Now we return to the linear examples. Okay. So we're considering now in this case we certainly so what if you want to apply the theorem above, then you need to know whether these guys respect coproducts and the adjoints of them. And the adjoints respect also respect coproducts. So tensor product by any projective modules respect coproducts, module respect coproducts, and tensor products by okay, maybe I should put a star here to make this remark to make more sense for this remark. Okay, so you may note that you will have both adjoint if you take only you have one adjoint if you take arbitrary projective modules here, and you will have two adjoints if you take finely generated projective modules. Okay, so you may say that this adjoint is realization with respect to this ring. Now, what about earlier result? Okay, I wouldn't say that this studying this function is very complicated, so it was in the thesis of Kelly, Shane Kelly. So it was assumed that R is equal to Z, but it's not important. You can take any R for his arguments, but so his thesis says nothing about the well-generated case, so this is new. So more general setting that was, to my impression, was nobody considered this. So if you take morphisms between finely generated projectives, then you say that you have a generalization with respect to universal localization of R. Yes, so we have some ring whose spectrum is open in the spectrum of R, and you have linearization with respect to this ring. And now what can you it appears that okay, several important examples come from various stable homotopy categories, and if you just take the usual stable homotopy category, then the nice thing for it then you have a T structure that is stable with respect to products, and so the adjoint to E, J, and F, J are some product functors. So you can apply the T structure criterion. Oh yeah, so it's stable with respect to products and also not degenerate. And so you can apply this T structure criterion. I don't want to return to it, but I can if you would ask me. So it just suffices to look at the stable homotopy groups of spectra, and if you take T consisting of coming from morphisms from a single morphism whose yes, I should correct this. So you take a projective resolution of the localization of Z, then you will get a statement code related to proposition 2.6 in the paper written by Busfield in 1979. So yeah, you should check whether the homotopy groups, so you should check the home condition for homotopy groups, for a certain, you check whether an object belongs to a certain subcategory. If you check that it's homotopy, a home condition for stable homotopy groups and the X1 condition for stable homotopy groups. Now, another question that was not really popular, actually. So, in the stable homotopy, motivic stable homotopy theory, so it was okay. It was clear that you have certain factoriality in the case where you should have it. Okay, but I don't think that anybody addressed the general question. So what do I mean by factoriality? So we have triangles of this sort. So the question is, when you have a triangle of this sort and you apply some exact functor, whether you have a decomposition with respect to some other semi-orthogonal decomposition. So whether the image triangle will correspond to certain semi-orthogonal decomposition. Okay, so the formulation of the corresponding statement looks rather terrifying, but I would say it's very natural. Okay, so the first thing that you need, so you need some transformations. So if you have adjoints, then periodic objects are universal. I've already told you are universally divisible with respect to tau to t lower star. So you need some class of transformations such that t lower star universally divisible objects will become t prime lower star universally divisible. That's and if you want this, it's natural to assume this condition. Now, if you also have this in the well-generated case, so and now if you want to your function to respect the whole semi-orthogonal decomposition, then you want you may say the torsion part to be mapped into the torsion part with respect to some t prime. Okay. So it means that so what is sufficient here to assume here that your this that we that you have you may say that you have compatibility conditions for two conjugate classes of transformations, and you also want your function to respect coproducts because the torsion parts is generated by coproducts, and then it works perfectly. Now, in this case, luckily, your functors are very simple. So if you want this compatibility, then you need to assume that your functors are linear, certainly. So for part one, you wanted to respect products of the corresponding size. So this assumption is automatic if we consider these morphisms are morphisms between finally generated modules. And to respect the whole semi-orthogonal decomposition, you also need your functor to respect our products. And okay, in particular, okay, so everything is if you consider the morphism between finite generated projectives here, it just suffices to assume that J respects coproducts, are linear respects coproducts. Okay, and this seems to be all. So there are just some references. So I will stop here. Thank you very much. And you are very much encouraged to ask questions. And any your comments, maybe that I missed some work about in this direction, or maybe the terminology is not optimal, that any such remark of this sort would be very welcome. Thank you very much.
Thank you very much, Mikhail. Let us all unmute ourselves and give the speaker a round of applause now. Right, so if you have any questions, please ask them. You had this theorem where if EJ star and FJ star preserved coproducts, then T periodic and the right perp of T periodic gave a semi-orthogonal decomposition. I was wondering if using this theorem, you could or one could construct some interesting or get some interesting semi-orthogonal decompositions on certain like categories in algebraic geometry, for example.
Sorry, so which theorem? This result or the well-generated one?
There was a theorem which said that if EJ star and FJ star, yeah, number two, yeah,
Two?
4.2, yeah,
This one or
yeah,
something?
this one, number. If you go down, number two, yeah, number two,
Oh yes, part two.
yeah. So can this result be used to get any interesting semi-orthogonal decompositions on, like I don't know, interesting triangulated categories arising in algebraic geometry, for example?
Yes, I hope so. You see, but possibly in concrete situations that were interesting for algebraic geometers, they already proved what they want. I just don't know.
Okay.
Okay, so if you have some candidate where you can try to apply it, I will be deeply grateful, certainly.
Okay.
So my motivation, okay, was in this R linear. Oh yeah, yes, and I would like to say, so if people want to obtain adjoints of this sort, so they usually say some words about infinity categories with some good models. In particular, this is how worked this paper, where the T-periodic paper. I don't know whether they are happy with formations of this sort. I'm not sure whether there are some categories which you would like to study, but you don't have any good enough model for this. Okay, so you get a generalization. I'm not, and which is rather easy to formulate. But maybe for all complicated cases, these more specific formulations are already sufficient. I don't know, unfortunately. Actually, so you see these inverting, so these functors corresponding are linear functors are quite natural, and it appears that nobody considered in them in general, but so for some other functors, maybe so they come from rather concrete categories, and then probably you have a model and so on.
Okay. Thank you.
Thank you.
Any other questions or comments? Sorry, I had one other question. So at the start of the talk, you made a comment, I think, that often one can't reconstruct the whole category just from the periodic objects or the pre-periodic objects. But I mean, are there interesting cases where one can reconstruct the whole category from the periodic objects?
I'm afraid that we misunderstood each other.
Okay.
What could I have said instead?
Okay. I think there was something about reconstructing the category just from the periodic objects.
So maybe I just told something. Oh no, the question is whether you reconstruct T, the set of
Oh,
transformations T
right,
known as
right.
periodic objects.
Sorry,
And
sorry. Right,
so
right.
this is rather trivial observation that T is not unique. So you can have yes, a large class of T's corresponding to a single class of periodic objects.
Right, yeah, sorry. Yeah, not reconstructing C dash, not reconstructing C. Okay.
So C is fixed, but T
Mm.
can vary. Yes, so that's what I was saying.
Yeah, yeah, yeah. Okay.
I was also wondering if an ale could appear as periodic objects for some. I guess should be, but I'm not sure. An ale or the coil, if we have a T structure, can the ale be described as periodic objects with respect to some endofunctors?
So you see, yes. So the A is semi-orthogonal, so it can be described in this way for I think that it can be described in this way for some transformation, but so a priori, so the first thing I can think about is a transformation from zero or into zero, and this is not interesting from the point of this theory. So you can apply this theory when one of these guys is zero, but it becomes less interesting. And
I see.
also, so if you want a nail that is not shift stable, then you should consider probably should consider functors that are not exact, or T that is not shift stable. So this doesn't fit well with the significant part of my paper, but it could make sense to modify the assumptions and to try to describe certain ales in this way. So it could make sense, really.
Oh, thank you.
You're welcome.
Thank you, George. Do we have any other questions? If not, let's thank the speaker one more time.
Thank you.
Thank you all for coming. We have Lev Borisov from Rutgers speaking next week. Hope to see you there. Bye-bye.
Thank you. Goodbye.